We've spoken about how the gradient is somehow the natural first derivative of a multivariable function, so now let's talk about the second derivative. An n-variable function has n-squared second-order derivatives, which we can nicely arrange as an n by n matrix called the Hessian matrix. More precisely, the ith row and jth column will be the xi xj derivative of f, though Clairaut's theorem will tell us that even if we get this backwards, it'll turn out all right. For the sake of concreteness, let's say that f is a function of 3 variables, so that we can write down its Hessian as so. Along the first row, we get the xx, xy, and xz derivatives. Along the second, the yx, yy, and yz derivatives. And the same story for the third row. As an example, let's actually write down a function and compute its Hessian. In this case, let's use the function xy squared z cubed and evaluate at the point 2, 1, negative 1. First things first, we find the gradient, since we need to know the first-order derivatives to get to the second-order derivatives. Being a polynomial, this isn't too bad to compute. From here, we can now compute the Hessian. The first row consists of the x derivatives of the gradient in the same order they appear above. The second row are the y derivatives. And the third row, the z derivatives. Plugging in x equals 2, y equals 1, and z equals negative 1 gives us the following matrix. As written above, and as common with our derivative computations, we can talk about both the Hessian matrix at a point or in general as a function. Moreover, you may have noticed that the Hessian appears to have a lot of patterns or symmetry in it. And indeed, a matrix is said to be symmetric if it is equal to its own transpose. This is equivalent to saying that the ij entry of the matrix is the same as the ji entry, so we can switch around the rows and columns and get the same thing. Well, Clairaut's theorem tells us that switching the order of the differentiation shouldn't matter, and in the Hessian matrix that's the same thing as changing the rows and the columns. Hence, the Hessian matrix is always symmetric. We can see this firsthand in the examples at the top of the screen. The 1, 2 element is the same as the 2, 1 element, just as the 1, 3 element is the same as the 3, 1 element. And of course this applies to the 3, 2 and 2, 3 elements as well. Finally, if HF is the Hessian matrix of a function f, then the Hessian, sometimes called the Hessian determinant, is the determinant of the Hessian. Again, this could be a real number if the Hessian matrix is evaluated at a point, or a function if the matrix itself is left as a function. If we take the determinant of the Hessian matrix above, left in terms of x, y, and z, then we get the following. This might look terrible, and it kinda is, but we just apply our usual cofactor expansion to the matrix. It's just that now the terms are variables rather than real numbers. In this case, I'm going to expand along the first row, though by symmetry, that's the same as if I had expanded along the first column. And you can imagine it's pretty easy to make a mistake here, especially if you lose track of the exponents, so go slowly and go carefully. But something nice happens here, and every term ends up being of the form xy to the 4, z to the 7, so simplifying gives us this. So the Hessian matrix is going to be our correct notion of the second derivative of a multivariable function.